Have you ever wondered about the fizz in your soda or why we throw salt on icy roads? Well, the answers are all around us, kind of hidden in plain sight. Today, we're going to dive into the chemistry of solutions, the invisible science behind pretty much all the mixtures that shape our world.
So let's kick things off with a bit of a puzzle. What on earth could connect the bubbles in a can of soda to the dangers a scuba diver faces way down in the deep? I know, it sounds totally random, right? But trust me, the answer is locked in the fundamental chemistry we're about to unpack. Okay, first things first. Before we get to the cool stuff, we've got to get the basics down. So what is a solution really? Let's make sure we're getting the mix right.
So a solution isn't just any old jumble of stuff. In chemistry, it's called a homogeneous mixture. And that word homogeneous is key. Homo means same. It means that once it's all mixed up, you can't see the individual bits and pieces anymore. The whole thing is perfectly uniform, right down to the molecules.
This slide nails the difference perfectly. So, on the left, you've got salt dissolved in water. You can't pick out the salt, right? The whole glass of water is salty. That's our solution. But then on the right, you got a bowl of trail mix. You can easily see the nuts, the fruit, all the different parts. That's a heterogeneous mixture, and that is not a solution.
And every single solution has two main players in the game. You've got the solute, that's the stuff that gets dissolved, like the salt, and then you have the solvent, that's the stuff doing the dissolving, like the water. You put them together, you get a solution. Simple, right?
Okay, so now we know what a solution is. But how do we, talk about them? I mean, if you add 1 teaspoon of sugar to your coffee versus, say, 10 teaspoons, they're both solutions, but they are obviously worlds apart. And that brings us to how we measure a solution's strength.
And that difference is all about a little something called concentration. When there's just a little bit of solute, we call the solution dilute or weak. When there's a whole bunch of solute packed in there, we call it concentrated or strong. It's really just the ratio of the stuff you're dissolving to the stuff you're dissolving it in.
Now, of course, chemists have to be super precise, so they use specific terms like molarity and molality. Now, a mole is just a standard way to count particles. Don't worry too much about that. The really important difference here is subtle but crucial. Molarity, with an R, measures the solute against the volume of the entire solution, solute and solvent together. But molality, with an L, measures the solute against the mass of only the solvent. It's a tiny difference in spelling, but a big one in the lab.
All right, so solutions aren't just a free-for-all. They actually follow very specific, very predictable rules. And once you understand these laws of liquid behavior, you start seeing this chemistry absolutely everywhere, from your kitchen counter to the bottom of the ocean.
And one of the biggest rules is Henry's law. Let's just break that down. All it's really saying is that if you crank up the pressure of a gas on top of a liquid, you can force more of that gas to dissolve into the liquid. More pressure, more dissolving. That's the gist of it. And guess what? This is exactly what's going on inside a can of soda. Before you open it, it's sealed under super high pressure, which crams a ton of carbon dioxide gas into the drink. The second you pop that tab, whoosh, all that pressure is gone. The liquid can't hold on to all that gas anymore, and the CO2 makes a run for it as bubbles. That fizz you see in here, that is literally Henry's law in action.
Okay, so another big one is Raoult's law. And this is where it gets kind of cool. Just by dissolving something in a liquid, you actually make it harder for that liquid to evaporate. It's like the solute particles are little roadblocks at the surface, physically getting in the way and stopping the solvent molecules from escaping. This lowers what we call the vapor pressure. And this one simple fact has some really, really big consequences. And this, my friends, is where things get super weird and interesting. It turns out that some properties of a solution don't give a hoot what you dissolve in it. They only care about how many particles you add. It's this strange, powerful idea about a solution's group personality.
These special properties are called colligative properties, and it's a wild concept. It literally doesn't matter if you're dissolving table salt, sugar, or some other random chemical. For these specific things, the only thing that matters is the number of particles you've tossed into the mix. It is all about quantity over quality.
And there are 4 big ones you'll see. When you add a solute, you lower the vapor pressure. That, in turn, makes the boiling point go up, and it makes the freezing point go down. And it also creates something called osmotic pressure. Just remember, all 4 of these things happen just because of how many particles are there, not what kind of particles they are.
Okay, enough with the theory. Let's bring this all back down to earth. How does all this chemistry actually pop up in our daily lives? You're going to be surprised how often you see this stuff at work. So let's circle back to our original puzzle.
What do soda and scuba divers have in common? It's Henry's law. As a diver goes deeper, the intense water pressure forces nitrogen gas from their air tank to dissolve into their bloodstream. If they come back up to the surface too fast, that pressure drops suddenly, just like opening a soda can, and all that nitrogen gas comes rushing out of their blood as tiny, dangerous bubbles. That condition is famously known as the bends.
And what about those colligative properties? Oh yeah, they're everywhere. You ever add salt to your pasta water? You're raising the boiling point, so the water gets hotter and cooks the pasta faster. Why do we salt icy roads? The salt dissolves and lowers the freezing point of water, forcing the ice to melt even when it's cold out. Antifreeze in your car's radiator? Same exact principle. And osmotic pressure? That's how plants are strong enough to pull water up out of the soil through their roots.
And just to show you how absolutely wild solutions can be, get this. The metal palladium can actually form a solid solution by absorbing hydrogen gas. How much? Over 900 times its own volume. Just try to picture that for a second. It's an amazing reminder that solutions aren't just about liquids.
So we'll leave you with this final thought. This whole idea of colligative properties, that some of the most basic behaviors of matter depend not on what a particle is, but simply that it exists in a group, that's pretty profound, isn't it? It suggests that matter has these collective properties, where the crowd itself behaves differently than any individual in it. Kind of makes you wonder, what else in the universe works that way? Something to chew on. Thanks for joining us for this explainer.